Welcome to Olympiad Math for Year 5. This is Lesson 10, we'll learn magic squares. In this lesson, we'll learn the basic construction methods of magic squares. A magic square is a widely known mathematical puzzle. According to legend, during the time of Emperor Yu the Great, floods frequently occurred in the area around the Yellow River and the Luo River in ancient China. While Yu was working to control the floods, a divine turtle emerged from the Luo River with 9 markings on its shell, see the left image below. Later, these markings were represented using natural numbers, as shown in the right image, and the diagram was called the Luo. The fascinating thing about the Luo is that the sum of the numbers in each row, each column, and both main diagonals is the same. Such a numerical arrangement is generally called a magic square. In the Southern Song dynasty, Chinese mathematician Yang Hui gave it the name vertical and horizontal diagram. The earliest known magic square outside of China is a 4x4 square inscribed on a temple tablet dedicated to the deity Gatotkaca in Khajuraho, India. European study of magic squares didn't begin until the 14th century, nearly 2,000 years after China. The Lo Shu is a 3x3 magic square, a square made of 3 rows and 3 columns. In general, if a square of n rows and n columns is filled with n square consecutive natural numbers, with no repetition or omission, and arranged so that the sum of each row, each column, and both diagonals is the same, then this arrangement is called an n-order magic square. The common sum is called the magic constant, and n is the order of the square. Magic squares have fascinated countless math enthusiasts. Even great mathematicians like Leonhard Euler and the famous physicist Benjamin Franklin were intrigued by them. The largest known magic square constructed to date is a 1256 order pan-diagonal magic square, invented in 1990 by a high school teacher in Wuxi, China. When the United States launched Voyager 1 and Voyager 2 in 1977 to explore extraterrestrial civilizations, the spacecraft carried not only recorded greetings to alien life, but also a collection of images. Among these was a picture of a 4x4 magic square. There are many different methods for constructing magic squares. In this lesson, we will introduce a few basic methods. Example 1. Construct a 3x3 magic square using the numbers 1 to 9. Method 1. For convenience, let us use the 9 letters A, B, C, D, E, F, G, H, J to represent the 9 numbers, and place them into the grid. First, find the magic constant. According to the definition of a magic square, the sum of the 3 numbers in each row, each column, and each diagonal must be equal. This common sum is a very important value and should be calculated first. 1 plus 2 plus 3 and all the way up to 9 equals 45. This is the total of all numbers in 3 horizontal rows, or equivalently, in 3 vertical columns. Therefore, the sum of the 3 numbers in each row or each column is 45 divided by 3 equals 15. Thus, the magic constant is 15. Second, determine the center number. Careful observation of a 3x3 magic square shows that the most important number is E, located in the very center, because it is used most frequently. 4 lines pass through it. But what exactly is the value of E? One way to find it is to write down the sum equations for the row, column, and both diagonals containing E. Add these 4 equations together. Since the sum of the 9 letters is 45, we get E equals 5. This means the center square should be filled with 5. Another way to think about it, among the numbers 1 to 9, there are 8 different sets of 3 numbers that sum to 15. In these combinations, the number 5 appears 4 times, more than any other number, so it should be placed in the center. Third, determine the 4 corner numbers. The four corner positions, A, C, G, J are also important, because each is used 3 times. Looking at the 8 combinations above, the numbers that appear exactly 3 times are 2, 4, 6, 8. These should be placed in the four corners, making sure that the numbers on each diagonal sum to 15. Finally, fill in the remaining spaces. The remaining pairs of numbers that sum to 10 are 1 plus 9 and 3 plus 7. Place these into the remaining 4 spaces, taking care to balance large and small numbers evenly, and you will obtain a complete 3 times 3 magic square. The magic square students create may not look exactly the same as the low shoe square. In fact, there are 8 forms of the 3 times 3 magic square. This happens because in step 3, when placing 2, 4, 6, 8 into the four corners there are 8 different possible arrangements. We can also see that the 4 squares in the top row of the arrangement chart can be obtained by rotating the first square 90 degrees counterclockwise repeatedly. By swapping the first and third columns of each of these 4 squares, we obtain the 4 squares in the bottom row. So although there appear to be 8 different forms, in essence they are all the same magic square. Method 2.
Yang Hui
Method. The ancient Chinese mathematician
Yang Hui
in his book Continuation of Ancient Methods for Extracting the Marvelous, described an arrangement method in these words: 9 numbers placed in a slanted arrangement, swap top and bottom, exchange left and right, push the 4 even numbers out to the corners. As shown below. In other words, you first arrange the 9 natural numbers in a slanted diagonal form so they form 3 rows and 3 columns. Then swap the top and bottom numbers, 1 and 9. Swap the left and right numbers, 7 and 3. Push the 4 even numbers to the 4 corners. Following these steps produces a complete 3 times 3 magic square. For this magic square's structure, Chinese folk tradition has a mnemonic rhyme: 4 seas, 3 mountains, 8 immortal caves, 9 dragons, 5 suns, 1 lotus branch, 2 and 7, 6 brothers admire the half moon, around the circle, the full moon of 15. By choosing a different starting point and direction for the 9-number slanted arrangement, you can also obtain other variations of the magic square. Method 3, the Lowbury method. The Frenchman
Simon de la Loubère
summarized a simple and effective way to construct odd-order magic squares, now known as the Lowbury method. It can be condensed into this mnemonic: 1 at the top row's center, then upright keep your venture. Out the top. Drop down below, out the right. Leftward you go. If a cell is already taken, go straight down without hesitation, the same for upright overlaps, keep the rule in rotation. Here is the step-by-step explanation. First, place 1 in the top row's middle cell. Second, move up and to the right for each next number. Each time, place the next number 1 row up and 1 column to the right from the previous number. Third, if moving up goes outside the top boundary, place the number at the bottom cell of the same column. Fourth, if moving right goes outside the right boundary, place the number at the leftmost cell of the same row. Fifth, if the target cell is already occupied, place the number directly below the previous number instead. Sixth, if moving upright leads to an already occupied cell outside the grid, follow the same rule, place it directly below the last number. Following these rules, you can fill in numbers 1 to 9 and a 3 times 3 magic square will appear as if by magic. Try it yourself. Using the Lowbury method, construct a 5 times 5 magic square. Method 4, Batchett's method. Batchett's method, also called the diamond method, applies to magic squares of odd order. The steps are as follows. First, draw the layout. Draw a 3x3 square. Then extend the figure outward by adding protruding, step-shaped blocks on the top, bottom, left, and right sides. Second, fill in the numbers. Place the numbers 1 to 9 in sequence along diagonal lines within the diamond-shaped, step-shaped pattern. Third, shift to fill the empty spaces. Move the numbers that lie outside the central 3x3 square into the corresponding empty spaces inside, shift the top part down, the bottom part up, the left part to the right, and the right part to the left 3 cells each time. This produces a 3x3 magic square. When filling the numbers, if the starting point or filling direction is changed, the shifting step will still produce a valid 3x3 magic square. Try it. Use Batchett's method to construct a 5x5 magic square. Example 2. Fill the 9 numbers 7, 10, 13, 16, 19, 22, 25, 28, and 31 into the grid on the right so that the sum of the 3 numbers in each row, each column, and each diagonal is the same. In example 1, the numbers 1 to 9 form an arithmetic sequence. In this problem, the 9 numbers to be placed, 7, 10, 13, and so on up to 28, 31, also form an arithmetic sequence. Is it possible to arrange these numbers into a 3x3 magic square so that the sums of the numbers in each row, column, and diagonal are all equal? Let's try using the Yang Hui method, the Lowbury method, or the Batchett method. Here we will present the Yang Hui method as following. 9 numbers placed diagonally. Swap top with bottom, left with right. Push in from 4 sides. In the square above, the sum of the 3 numbers in each row, column, and diagonal is 57. As for the Lowbury method and the Batchett method, try them out yourselves. From this we can see that any arithmetic sequence can be arranged into a magic square so that the sums of the rows, columns, and diagonals are all equal. For a non-standard magic square, the sequence does not have to start from 1. Example 3, place the numbers 3.3, 3.7, 4.1, 8.9, 9.3, 9.7, 14.5, 14.9, 15.3 into the 3x3 grid so that the sum of the 3 numbers in each row, each column, and each main diagonal is the same. The 9 numbers here do not form an arithmetic sequence. However, if we group them in order into 3 groups of 3 numbers each, we see that every group forms an arithmetic sequence with a common difference of 0.4. Looking more closely, the last number of each earlier group and the first number of the next group differ by 4.8. Could such a set of numbers be arranged into a magic square? Let us give it a try. Here we will display Batchett's method. Draw the layout, and fill in the numbers. Shift to fill the empty spaces. In this arrangement, the sum of the 3 numbers in each row, column, and diagonal is 27.9. Please try arranging the numbers using Yang Hui method and the Lowbury method as well. This shows that numbers with the above structure can also be arranged into a magic square. Example 4. Construct a 4x4 magic square using the numbers 1 to 16. This method applies to doubly even magic squares, orders divisible by 4. First, find the magic constant, which is 34. Second, fill the numbers 1 to 16 in order into the empty cells of the 4x4 square. At this point, the sums of the 2 diagonals are already equal to the magic constant 34. Third, keep the diagonal numbers unchanged. For the remaining numbers, swap the non-diagonal numbers in columns 1 and 4. Swap the non-diagonal numbers in columns 2 and 3. Then swap the non-diagonal numbers in rows 1 and 4 with those in rows 2 and 3. This produces a 4 times 4 magic square. From the arrangement above, you can see that the diagonal numbers remain fixed. The transformation pattern is as follows. For singly even orders, like 6 times 6, you can explore the Strachey method or Conway's Lux method, both available on Wikipedia. Here are the practice problems for today. Thank you for watching and hope you enjoy your math today.